Hi there. My name is Jason Gu, and during the summer after my junior year of high school, I was accepted to attend the International Summer School for Young Physicists, or ISSYP. Now, at this program, I had the wonderful opportunity of working with theoretical physicist Finn Gray on a small group research project. So today, I'd like to take the next couple of minutes to explain a little bit about the work that I completed. Now, our project involved creating a black hole analog using water flow with sound and surface waves. So on the screen now are some pictures of the posters taken from the ISSYP poster session, where we had the opportunity to present our research in front of hundreds of theoretical physicists. So let's take a look at each component of our research separately, starting first with some basic general relativity and black hole information. Now to begin, Einstein's theory of general relativity is still an extremely young field of physics, with much of its specifics still unknown to us and being researched as we speak. However, the basics of general relativity state a couple of main things. First, that the gravitational pull that objects feel, such as a ball dropping to the ground or planets orbiting our sun, are all due to the fact that massive objects warp the curvature of what we know as space-time. This is mathematically expressed in Einstein's field equation, which essentially describes how mass curves spacetime, as well as how curvatures in spacetime dictate the path of mass. Now, one important thing to note is that this capital G here, which is known as Einstein's tensor, is dependent on spacetime itself, as well as something called a metric tensor, which is denoted by lowercase g. And it's this quantity that we will research further in the upcoming slides. But before we get to that math, we need to understand a little bit about black holes, starting with something called a light cone. Now, what a light cone is essentially a graphical representation of where an object can and cannot be in the foreseeable future. If we take a look at this diagram, we can see that the cone both has spatial axes, the x and y, as well as time axes denoted by this ct here. Now, the interesting thing is that when black holes, or regions of extremely dense mass and gravitational pull, curve spacetime enough, the light cones of objects traveling near these black holes can actually rotate and tilt as well, as shown here. And at a certain point known as the event horizon of a black hole, the light cones tilt so much that no matter how fast you go, even at the speed of light, which is our speed limit of our universe, nothing can move spatially to escape the region. They can only move up and down in time. Now, the interesting thing is that we don't need to be in outer space or to be completely sucked into a black hole to observe these properties. We can actually form a very accurate model with things here on Earth. So let's start with static black holes, or black holes that don't rotate. Say, for example, that I have a giant tank of water here, and that has a pump to keep a constant volumetric flow rate. Basic fluid mechanics shows that water moving through smaller cross sections of the tank begin to move faster and faster. And as the area increases, the water slows back down on this left side. Now let's assume that we have a waterproof microphone that's able to emit sound waves inside of the tank. Since the speed of sound is constant in a given liquid, the sound may be able to combat the water current flow on the slow sides to reach the left side of the tank here. However, if the water were traveling fast enough in these tighter areas, sound emitted from these places may not be able to travel fast enough to overcome the flow of water. And we wouldn't actually be able to hear anything if we were to stand on the left side of the tank. So in this case, these regions of fast-moving water that prevent sound from escaping would be analogous to our event horizons from earlier. And we can actually formulate equations to represent our situation. So to start, we'll begin with a sort of foundation equation, which essentially relates distances in certain spaces, which are called manifolds, to our changes in space-time, as well as a metric tensor that we were talking about earlier. Using the property of sound waves and traveling water, we can simply relate our distances on our manifold to things such as the space itself, water current, as well as the speed of sound. Now, we can actually solve for our metric tensor, which involves matching the coefficients of each of these variables to get a sort of matrix. So the acoustic metric tensor, which is the metric tensor describing sound, is extremely helpful as it describes the spatial situation we're analyzing in solely a 4x4 table of values, with an important top leftmost index, which will help us find our event horizon. By comparing this metric tensor with actual black hole metric tensors, namely the Schwarzschild metric, we can solve for the event horizon to be when the top leftmost index is equal to 0, or when the speed of sound is equal to the speed of the water. And this makes perfect sense. We were talking about earlier how when water is flowing fast or faster than the speed of sound, the sound won't be able to overcome the water current, which produces the event horizon that we calculated. However, another type of black hole are what known as stationary black holes, which basically involve a rotational component, making them look a little bit like a vortex or a funnel. We can apply our water analog once again to these types of black holes, with an idea as simple as a toilet bowl draining. So let's take a closer look once more at the derivation behind this type of black holes analog. Because we're still working with our metric tensor in the same space of water and sound as before, we begin with the same two equations that describe the space under analysis. However, this time, the velocity will be split between two directions. One showing us how fast the object moves in the radial or away from the center direction, and the other showing how fast it rotates. A similar process to the first leads us to our solution for the stationary acoustic metric tensor, which can be seen down here. Now, the event horizon radius is still quite simple to solve for. It's when the velocity component moving away from the center is equal to the speed of sound, or basically when sound can't escape. However, in this case, the top left index of our old metric tensor becomes something unique to stationary black holes, what's known as the ergosphere, who has an equation that can be seen here. Now, the ergosphere is a radius which, closer to the center than the ergosphere radius, rotation along these stationary black holes is inevitable. However, inside the ergosphere region and outside of the event horizon region, objects can still hypothetically escape by traveling quickly away from the center. So think of it as kind of an event horizon, but for rotation instead of escaping. Now, I know this was a theoretical physics program, but a little bit of experiment can never hurt, right? So at the Perimeter Institute, we created a static black hole analog by creating sort of a waterfall in a box, perhaps inspired by our Niagara Falls trip a couple days before, using surface perturbation waves instead of sound waves for convenience. Because the water speeds up as it falls down the waterfall, we can theoretically find a location where the sound will not be able to overcome the waterfall's flow, helping us to visualize the event horizon in black holes with simply a pump in a box. And that's exactly what we did. By shooting water drops onto the smooth water flow beneath, our surface waves, which move with a constant velocity in a similar way to how sound moves with constant velocity, can be observed to either overcome the water flow or completely brought to a halt. And using the rulers on both sides, we can calibrate where this level is. So after taking some data, just how close were we to what the math predicted from before? Well, using a data analysis software, we measured the velocity profile of the water along our black hole analog. Measuring the curvature of our waterfall, or our manifold, we can use the calculations that we shown previously to predict where our event horizon should be. As we can see here, our predicted event horizon location, which is shown in the dotted red line here, came extremely close to what we observed in this black line here, was less than a 5% margin error. And it's this part which truly excited me the most about our research project. While yes, it's amazing to be learning all the theory and the math behind black holes and working through a research problem with an amazing theoretical physicist, it's the fact that the theoretical physics, the work done with pencil, paper, and calculator, can physically be manifested in our everyday lives to represent the phenomena in the cosmos and universe that we would never be able to observe or see or experience otherwise. It's this aspect of our project that has truly led me to pursue a physics career in the future, and I hope I've been able to at least a little bit show you how powerful that process means to me, as well as to hundreds and millions of researchers worldwide. Thanks for watching.